Hello everybody, my name is Ben-Yaakov and I'm here to present a new design and concept of a switch capacitor DC-DC converter. Let me start off by giving acknowledgement to, first of all, Mr. Alexander Kushnerov, who is a master student at the Ben-Gurion University, and he's been working on this subject, and his thesis is really related to switch capacitor converters. Another person who is deeply involved in this research and development of the concept is Mr. Meir Shashua. He is the CTO of Waves Audio, who is actually a partner of this project. The area of switched capacitor DC to DC converters is related in general to power electronics and power conversion systems, in which we have a electricity of one form that is transferred to another form. These systems could be either unidirectional or bidirectional, transferring energy from one port to another. The power conversion is required in all systems today, or practically all systems, since there are very few cases in which the load is connected directly to the source, being either a power line or a battery. The simplest way to regulate a voltage is by a linear regulator, in which we have a series element, typically a transistor or MOSFET transistor, that is adjusting the output voltage by actually controlling the difference between the input and the output. In most cases, we can assume that the same current is flowing through the series element and the load, and therefore we have same current flowing from the input voltage to the load, and this brings out a very simple expression for the efficiency. So inherent in each linear regulator is a efficiency limitation, which is expressed as the output voltage divided by the input voltage. Now, since in a regulator we want to adjust the output while the input is varying, consequently, in most cases, we are going to have a fairly low efficiency. Of course, there are some so-called low dropout linear regulators, meaning that they can sustain a small difference between input and output. This will be the difference V in minus V out. But, of course, the question is, what is the real input voltage? And you cannot keep it always very close to the output. The most efficient way to convert one voltage to another would be to use a so-called switched inductor. In this case, we are, in general terms, loading or charging an inductor with energy, and then when the switches are turned to the other direction, we are discharging this energy or part of this energy to the load. By this, we can transfer a controlled amount of energy between input and output, and therefore regulate the output voltage. It can be shown that this process is lossless, except, of course, for the parasitic losses involving the resistance of the switches and resistance of, say, the inductor and other parasitic elements. But in its basics, this is a lossless process. Another way to transfer energy from the input to the output would be to use a switched capacitor, or sometimes referred to as charge pump. In this case, energy is transferred to a capacitor, to a floating capacitor, and in the other position of the switches, this energy is transferred to the load. Shown here is an inverter, but of course, same principle can be used to realize both inverting converters, up converters, or down converters. Unfortunately, this process has losses which are inherent to the process, and this is something that I'm going to expand on, but this will be the main drawback of this approach. Now, considering the fact that energy efficiency is of prime importance, the question is, why is it that switch capacitor converter are still preferred in some cases? And the reason is that it has no magnetic elements, and therefore there are no problem of interference, and also for low power it can be fabricated as an IC both from the switches point of view and the capacitors. The disadvantage, as I already pointed out, is of course the inherent power losses and the relatively larger number of switches that is normally required over the switched inductor case. However, for an IC, this may not be a very limiting factor. Now, the inherent power losses is the subject of this work, and our attempt is to reduce these, but for that we really do have to understand the reasons for the power losses. Now, as I've already pointed out, switch capacitor DC converters could be designed for up converters, down converters, and in this case I'm showing a doubler, and in which a capacitor is charged to the input. This is the input, and then by changing the position of the switches, this charged capacitor is placed in series with the input, and consequently the output will be twice the input voltage. In this case, we have a converter which produces half the input voltage, and this is by putting the capacitor in series with the input, but in opposite direction, after it's being put in parallel to the load. So when, say, Q2 or the phase, the clock, phase 2 of the clock is on, the capacitor is connected to the load, and therefore it assumes the voltage of the load, and then when it is placed in series with the input, then in this case we have the input minus the output equals to the output, which brings out the relationship that the output is the input divided by 2. Now, going back to the question of losses, it can be easily shown that if we have a capacitor which is starting with a voltage V sub 2 and then connected to a voltage V sub 1, this process entails energy loss. The energy loss can be calculated by looking at the energy of the capacitor before connection, the energy of the capacitor after connection, and the amount of energy that has been transferred to or from the input or the voltage source, and the expression delta V square divided by 2 is very typical to the losses of system like this. And what it means is that whenever you have a voltage difference between the capacitor and the voltage source, there will be an energy loss proportional to the square of this difference. The same thing goes for the case in which you have two capacitors, one charged with a voltage of V sub 1, the other one V sub 2. Again, we find that the energy loss is proportional to the voltage difference square. So when we build a converter based on the switch capacitor technology, we have to take into account that there will be some energy losses, which will increase as the difference between the input voltage and the capacitor voltage, and of course the output voltage is changing. Now typically we would like to have a regulation. In the case of regulation, we want V sub out, the output voltage, to be different, of course, from the input and regulated to a fixed value. This requires some means of control, which are typically done by adding a resistance in series to the capacitor, and thereby causing a partial charge and discharge of this capacitor to maintain the difference between the input and the output voltage. Unfortunately, this brings again the problem of efficiency, because as soon as there is a difference between the input and the output, the efficiency, of course, will go down. Now, of course, the efficiency is a function, as I've said, it's a function of the output voltage and what we call the target voltage. And I'm introducing here already cases in which the output is not necessarily equal to the input, but the output target voltage may be like a multiple or half the input voltage. Now, target voltage just can be made to be like quarter, three-quarters, and there are, of course, many other combinations possible, and this is done by involving a number of capacitors. For example, if you have three capacitors, as in this case, and the three are connected in parallel in one phase to the output, and then put in series, then we are subtracting from the input three voltages which are equal to the output, and this in the steady state will cause the output voltage to be 1/4 of the input voltage. And of course we can get some other ratios like the like 3/4 and many other ratios. Here we see a commercial unit. It's a microlinear LTC 1911, which is a switched capacitor regulator, and shown here are the performance in terms of efficiency in the case of a output voltage which is 1.8 volts and varying input voltage between 2 and 6. Now the target voltages of this unit are 1/2, like half, and 2/3. So when the input voltage is related to the output voltage through this ratio, efficiency is expected to be high because the voltage differences between the capacitor and the input and output is small. For example, if the input is around, say, 3.6, which is here, we see here a high efficiency peak because the required ratio is 1/2, and indeed this converter can be configured to have a 1/2 conversion as a target voltage. However, if the voltage is changing, I mean the input voltage is changing so that the required ratio is different from 1/2, a voltage difference develops between the floating capacitor and the input and output, and consequently, of course, the efficiency drops. So the point that is important to realize is that at the target voltages, we're going to have fairly high efficiencies because the differences between the voltages that the capacitor sees in the two switch modes are small. While if we are far away from the target voltages, efficiency will drop, and as we can see here, we'll see efficiencies below 70%. Now, the objective of this project was to develop a conversion system that has many target voltages. And the distance between these target voltages be kept small. By this, we are going to have, or if this can be accomplished, we are going to have a fairly high efficiency all over the output to input ratio, because always we are close to a target voltage, and at a target voltage, of course, because the capacitor sees a small voltage difference, the efficiency will be high. The approach taken in this project in order to get a high resolution is to rely on a number system. We call it the extended binary number representation that has features which are required to get high resolution. Now, once we identify this binary system, we found a way to translate this binary system into a topology of a switched capacitor converter that will follow this system, and consequently we ended up with a performance of a switched capacitor, a DC to DC converter that has many target voltages. So I'm going to leave for a while the issue of switched capacitor and go for a minute or a few minutes to the question of binary systems, binary numbers, and the extended binary system that we have developed here. Now, we all are familiar with binary numbers, but there is a extension to the regular binary numbers, and that is the binary fraction, in which a number smaller than 1 can be represented as a sum of power of 2, while the power is negative, meaning that we have smaller than 1 numbers. Now, in this case, we have 2 coefficients, like in any binary number, 0 and 1, and by selecting, of course, this coefficient, we can get any number smaller than 1 with the resolution which is depend on the number of bits that we are using. Just an example, suppose we would like to express 5/8, then in this case we have the first, since coefficient is 0, then we have 2 to the power of minus 1, which is 1, so this is like half. We have 0 here, and this is 1/8, and the sum of these two is, of course, 5/8. As in the normal binary number representation, we can express this number as a code, as a binary code, having a coefficient or having integers of 0 and 1 that represent the coefficient of each term. An extension to the fractional binary number representation is the signed binary number, which in the past has been shown actually for positive powers of 2. And in this case, we have coefficients of the terms which can extend not only to 1 and 0, but also to minus 1. What it brings about is the possibility to represent the same number in different ways. For example, the number 5 can be represented as 2 to the power of 0, which is 1, plus 2 to the power of 2, which is 4, and the code would be 0, 1, 0, 1. However, the same number can be represented differently as 1 to the power of 1, which is 2, and then to the power of 2, which is 4, and then in this case we have to the power of 0, but with a minus sign, so we are actually subtracting this term, and therefore we have 4 plus 2 minus 1, which is again 5, and it is a different representation for the same number. The code in this case will include 0, 1, 1, and minus 1, which of course is not found in the regular binary, but it's in the signed binary we found this minus 1. Now, the extended binary representation is sort of including the fraction part that I've mentioned and also the sign part. We're talking about numbers in the range of 0 to 1. And the representation here includes actually two parts. One is a fixed coefficient, and then a sum of these binary fraction terms. The first term can take the values 0 or 1. The coefficient of the binary or the fractional binary terms can take the values 1, 0, and minus 1, similar to the signed binary representation. So in this case, a number like 5, 8 can be written, of course, in different ways because it's a signed binary. And let's take an example. It can be written as to the power of minus 1, minus 2. This will be like 1/2. This will be 1/4, minus 1/8, and this is 5/8. And of course, this will be another possibility and another possibility, and the corresponding codes would be as shown here. An important result of this research is providing an answer to the question of how many codes and how many possibilities can be generated for a given fraction. Now, in order to find this number, we start with the regular binary representation or fractional binary representation of the number. As an example, we consider 5/8, which is in the regular fractional binary representation will be 2 to the power of minus 3 plus 2 to the power of minus 1, which is 1/2 plus 8, which is 5/8. Now, starting with this, we can, let's go over to this case. Starting with a 1 in one column, we can add to it another 1, which is basically adding 2 to the power of minus 3 here. Now, this is a regular binary addition, so 1 plus 1 is 0 plus a carry, which is 1 here. However, in order to keep the same value of the number, we have to subtract the same value that we have added, and we do it, however, in this case, by adding a negative coefficient here. So minus 1 stands for minus 1 times to the power of minus 3. So by this, we generated an extra number or extra code for the same value of number 5/8. Now, repeating this on each of the ones in the code and on each of the ones that are generated by this process, we end up with a few codes which represent the same numbers. All these codes represent 5/8. The question is, of course, given a certain resolution, that is a certain number n, how many codes will be generated for each number or each fraction? Now, since we have already said that each of the ones will be replaced by a -1, and then will actually, in each 0 or place of a 0, will generate a 1 as a carry, then it turns out that aside from the original value, for each position of this n resolution, we're going to generate an extra code, and consequently we can say that the total number of codes that can be generated from a given binary number is at least n plus 1. I'm saying at least because it turns out that there are some, in some cases, it's possible to generate extra codes, but this is not important for our discussion here. Another important corollary of this generation algorithm or code generation algorithm is the fact that whenever you have a 1, there's always be at the same column a -1. And this is again is because that 1 is replaced in order to generate other codes by a -1. And consequently, if you look at each of the column, you'll see both positive and negative ones, and this has an implication to the development of the converter or the switched capacitor converters that I'm going to get into fairly quickly. Just to summarize what we have seen here, taking the case of resolution of 3, remember A0 is different from A1 to A3. These are the coefficient of the to the power of the negative numbers. This table summarizes all the codes for the ratios you can get in this case, like 1/8, 2/8, 3/8, etc. And these are the corresponding codes. In the case of 1/8, we see that we have 1, 2, 3, 4 possible codes. N in this case is 3, n plus 1 is 4, and this is exactly what has been predicted. In some cases, like for example in the 5/8, we have 1, 2, 3, 4, 5 codes, and there is an extra code here, which again is not important. I'll refer to it a little bit later. In some cases, we seem to have a limited number of codes, for example, for the 4/8. Now, the reason for that is that the 4/8 is basically 1/2, and to generate 1/2, you really don't have you need a resolution of 3. There isn't enough to have a resolution of 1. So in this case, the resolution is 1, and 1 plus 2 is 2, so we have 2 equations. Now we go back to the question of switch capacitor converters. We want to generate or to develop a converter which will have many target voltages. We found a way to have a number which has many. Let's have a look here. We found a way with a resolution of 3 to get all the ratios of 8 between 1/8 to 7/8. And now we are going to use this representation to translate it into a switch mode capacitor converter that, of course, will have the same features of the code itself. The rules for converting the code to a switch capacitor topology has a number of sequences that we have to follow. The first one is to realize that this number, which is like the 3/8 in this case, represent the ratio of the conversion. This will be the target voltage of the converter. Now, each of these coefficients now, the n coefficient, is associated with a capacitor. A0 is associated with the input voltage. So this is the input voltage, and this is associated with the capacitor. We have, in this case, for n equal to 3, we have 3 capacitors. Now, the coefficients of the codes, like 1, 0, for the input part, say whether the input is connected or not. For the 1, for this case, the input is connected. In this case, the input is not connected. For the capacitors, 0 again means that the capacitor is not connected, while 1 means that it's connected in one direction, and this will be a discharging direction. We'll see it in a minute. While a -1 means that it's connected in the opposite direction. So the capacitors are connected in series to the load, and possibly with the input if the coefficient for a given code is 1. So this is actually summarizing the rule that I've already referred to. And in order to really understand what all this thing means, let's have a look at the actual implementation of these rules. We are starting with codes. Each code represents the number or the fraction 3/8. Each code is associated with a topology. So if we have 1, 2, 3, 4, 5 codes, we have 5 topologies here. Each topology follows the connection described by the code. So, for example, if you look at the first line, 1 implies that the input is now connected. -1 implies that the capacitor C1 is connected in such a way that it is charging. And then A2, which is associated with the second capacitor, is 0, meaning that the capacitor for this topology is not connected, while for the third capacitor, it's again connected in charging position. Obviously, due to the meaning of this code, when you combine Vin plus the capacitors, you expect to see the number, and this would be correct if the capacitors are charged to the binary weighting ratios. That is, C1 is charged to half the input voltage, C2 is charged to the 1/4 of the input voltage, and C3 is charged to 1/8 of the input voltage. So in this first case, we have the input voltage minus half of the input voltage and minus 1/8 of the input voltage, and of course this will be like 8/8 plus minus 4/8 minus 1, and this is equal to 3/8. The same goes for the other lines or for the other codes. Let's take an example, this particular one. Again, we have 1 here, so input is connected. In this case, capacitor is connected in the charging direction, capacitor 1, capacitor 2 also, and capacitor 3 in the discharging. In the case when we have 0 coefficient of the A sub 0, the first term, the input voltage is not connected, so this is this case. And as you can see, we have just the capacitor connected to the output. Again, C2 is charged by 1/4 of a Vin minus plus a 1/8, and this is again 3/8 of V in. So what we found in this research, and represented here, is that if the capacitors are charged to half V in, quarter, and 1/8, and then they are connected in a topologies which follow the code for a given fraction. Here shown for 3/8. Of course, we have different codes for the other fractions, like 1/8 or 5/8. So then, for each connection, the output will be the correct or the required conversion ratio, that is, in this case, 3/8 of V in. Now, obviously, one would ask two very important questions. Number one is whether this system is stable. That is, suppose we are charging the capacitors to these voltages, and then we are connecting them as shown here. Will they sustain the same voltage, or will it change with time, either drop or increase from the required values? Now, as it turns out, this is correct, and not only that, we'll show in a few minutes that even if we start this sequence of connection with a capacitor without any voltage across them, they will eventually stabilize and converge to the required value, that is half, quarter, and 1/8 of the input voltage. The reason for this sort of surprising result is that these topologies are basically representing codes, and each code can be shown to represent an equation. And already we have said that we have here n+1 code at least, and so we have n+1 equations and n+1 topologies. Another important result that we have already discussed is that when we go through these sequences, we find that a given capacitor will be charged in one topology and then discharged in another topology, so that we have sequences of charging and discharging, and by this there is at least a chance for the voltage to be retained at the required value and not change or drop to zero. But as I've said, the situation can be shown to be rigorously correct by a mathematical terms, providing that we are going through all these sequences and not missing any of them. That is, if we start with, or for the case of 3/8, we'll go through all the codes, all the n+1 codes, and then start again with n+1 codes. We are going to retain the value of the capacitor voltage, and of course at that time we are going to have an output voltage which is 3/8 of the input voltage. So is there a unique solution, and is this solution the required value of voltages across the capacitor? And what happens if we start with a capacitor which has 0 voltages, and will they maintain the voltage during transient or change of load? Now, the answer to this question is actually the set of these algebraic equations. one can look at each one of these connections as an analog representation of an equation that says that the input voltage plus the voltage of the capacitor connected is equal to the output voltage. And this will be this line. Another topology, which corresponds to another line in this code, is another equation. So by going through all these topologies in sequence, we are forcing the capacitors to obey this set of equations. And the question is, of course, whether these equations do have a solution, and what is the solution of these equations. Luckily, we have enough equations. The number of unknown is the voltage on the capacitor plus the output voltage, which we at this stage assume that it is unknown. What we know is the input voltage and the way the capacitors are connected with the output in series. Now, by manipulating this equation and normalizing it, we can get a matrix expression or form of this equation in which x sub 1 and 2 to 4 are actually normalized value, and this is the normalized to the input voltage. Now, for a linear equation of this form, according to a theorem by Kronecker and Capelli, there's going to be a unique solution if the rank of the original matrix is equal to the rank of the augmented matrix, and when the rank is equal to the number of unknowns. Now, an augmented matrix is the original matrix plus the column of the B matrix. This is the original matrix, and this is the solution matrix, and we add it to this matrix, and this is the augmented matrix. As it turns out, for all the combinations for the extended binary representation, all of them obey this theorem, and it implies that there is a unique solution, and this solution is indeed the expected one. Well, here are the capacitor voltages, and this is the output ratio, the output to input voltage ratio. It can thus be concluded that by following the topologies of the extended binary code, the capacitor will end up having the voltage according to the binary weight, and the output will resume the value of the code that the topologies are following. It is interesting to note that by switching the meaning of input and output, that is, if we connect a voltage source to what was up to now the input terminals, the output terminals, and put the load at the terminal that were up to now called the input terminal, we get the same set of equations with switched meaning of input and output. And of course, this set of equation has also a solution, which implies that the same configuration of capacitors can be used for step up also. So we have the way to boost an input voltage to a higher voltages, following, of course, 1 over this fractional value. That is, in the step down, we'll get 3/8 of the input, while in the step up we'll get 1/3 of the input voltage. To implement the concept, we do need switches that can connect the capacitors in the required position and with the input and the load. And in this project, we have used a discrete semiconductor switches rather than, of course, developing a dedicated ASIC for the purpose. And the basic configuration that is needed is a sort of a bridge across each capacitor that will enable the connection of the capacitor in either positive or negative direction. So for a resolution of 3, that is 3 capacitors, we have 12 switches which are required. The system was built using a bidirectional switches, which are the Maxim analog switches. This is actually the relevant part to the switch capacitor converter. This part is basically a sensing part just for the purpose of debugging and analyzing the performance. And the system, the experimental system, was driven by a microcontroller, a PIC, and here are the lines coming off the microcontroller through drivers which operate the switches. The system will beat for a high number of capacitors. The result that I'll show you is for 3 capacitors. Here is a example of a startup sequence. This is simulation, and this is experiment. In this case, the ratio was set to 3/8. Again, the system was changing the topologies according to the requirement of the 3/8 code, going from one topology to another, and starting from 0 output and 0 input and 0 output. Here is the startup sequence, and we see that within like few milliseconds, excuse me, the system is reaching steady state. The efficiency for each given transfer ratio that is set by the, of course, connection of the capacitors is, as expected, high, because we are at the target voltage. We have a target voltage of 3/8, so for this ratio the efficiency is high, and the same thing goes for another target ratio, which is 5/8. Now, obviously, the resistance of the switches, as well as parasitic effect, will cause dropout, especially for low load resistances. This is an experimental system in which the resistance of the switches was fairly high. Now, the efficiency, again, going back to the question of efficiency, can be analyzed by considering a simple equivalent circuit for the switched capacitor converter, which is pretty much similar to the linear regulator, in which we have a source which is the target voltage and the internal resistance, which is a function of, among other things, the value of the capacitors and the resistance of the switches. Efficiency, again, will be output, the real output voltage over the target voltage. Now, the key to the efficiency at the target voltage for a given load will be, of course, the value of our equivalent, because it'll have a voltage drop across it, and consequently a difference between the output and the target voltage. Now, we have examined the equivalent resistance of our experimental system and compared it to what would be expected from theoretical basis. In order to extract the value of this resistance, one can carry out experiments for different R out, and considering that the output voltage is just a function of the input voltage, like the source, and a voltage divider, by rearranging it, one can express the term of input voltage times output load, the load, and the output voltage, which is all are known, as a linear function of R out, which is also known, and R equivalent, which is, of course, still unknown. And by plotting this linear expression, one can get this value here, which is, of course, will be for y equal to 0 minus the intersection with the x, which is this value. So by carrying out this experiment and plotting the data using this linear regression, we obtained a value for the internal resistance of our experimental unit to be about 7 ohms. Now, this is consistent with the values of capacitor that have been used and the fact that the resistance of the switches that were used is 1.2 ohms. Now, one should bear in mind that, of course, we have a number of switches in series for each case, and consequently, the total resistance is indeed higher. Now, what about regulation? Obviously, in a practical application, one may wish to regulate the voltage to a given value, which might be off the target voltage. Now, we have examined in this study two approaches. One is the dithering, that is moving from one ratio to another, and the other one is the linear regulator. For the dithering case, we obtain a transfer ratio which is in between the target voltages by repeating the sequences corresponding to one target voltage, and then having a sequence of another target voltage. All these are codes of the 4/8 topology. So by weighing the contribution of each part, we get a ratio which would be different, or can be different, from each one of the individual contributors, and by changing this ratio, we can get, of course, regulation. This is, for example, a zoom on the output voltage for a continuous ratio and a dithered ratio, and here we see dithering between 3/8 and 4/8 in 2-to-1 ratio. The reason for the higher ripple here, this is, by the way, 10 millivolt per division resolution, is that we are moving from one configuration to another, and therefore there is some disturbance in the system. Another way to get regulation is to introduce a linear regulation in between the output of the switch capacitor converter and the load. By adjusting the voltage drop across the linear regulator to be about the value of the LSB, we can then regulate the voltage in between the two target voltages. This is, of course, will cause some efficiency drop, as would be expected, but in any case, if we need a output voltage which is different from the target voltage, then one would expect to have some losses. By having a linear regulation, though, we can reduce the ripple at the output and have a smooth regulation over a larger range by changing, of course, the target voltages of the switch capacitor part. To summarize what has been detailed in this presentation, we have developed a high efficiency, wide range switch capacitor converter by basing it on a fractional binary sequences. The binary resolution gives us a fairly close spread of the target voltages. The downside, of course, is the relatively larger number of switches that are required in order to get all these configurations. Aside from what has been presented here, we have studied, and we do have data on other issues like the question of convergence and a more theoretical, in-depth study on the losses. And also, we do have a means to reduce the ripple by choosing a specific sequence that the topologies are changing from one state to another. This brings me to the end of this presentation. Thank you very much for your attention. Okay, are there any questions, please? Okay, I'll thank you very much for your question, which is a good one. I'll repeat it just in case it was not recorded properly. The question was whether we do have to go through all the sequences, especially when we do have some redundancy here, because as we have said, that there is a need for n+1 codes in order for the system to be solvable. And here we have an extra code, and the question is whether we do have to go through all the codes. And the answer is that, in fact, in our study, we found out that there is a advantage in using some additional codes by repeating some of the basic codes. Now, the reason for the advantage in doing that is that for minimum ripple, you'd like to have a sequence of charging, discharging, and then preferably charging again. So by spreading out the sequences and plugging in repeating some of the sequences, it turns out that one can get a situation. In fact, in the particular case of n times 3, we have a 8-length sequence in which for each capacitor we're going to have a charge-discharge charge-discharge sequence, which will of course minimize the ripple by not leaving the capacitor in one position, like just charging and then for a number of sequences and then discharging. So there is a advantage in using all the possible codes, and in fact adding some and rearranging it in such a way that it will have a charge-discharge sequence. Is there another question? That's Charles.
Looking at the sequence tables that you're showing here, one can see that there are cases where are less equations than n minus 1.
N plus 1.
N plus 1. Can you comment on that?
Okay. Well, if we look at the case of, say, 4/8, for example, this is indeed the case. and I think I mentioned it, but it's important to realize that 4/8 is in fact a case in which the resolution is only 1/2. That is, although showing here are the two extra terms, but the resolution is only 1/2, so that there is a need for one capacitor to carry out this ratio. In fact, this is the case in which you have a capacitor which is connected in parallel to the load and then put in series with the input. And in this case, since there is a need to maintain the voltage of only two elements, that is the voltage of the capacitor and the output voltage, so we do need only two equations, and indeed we do have these two equations. Okay, thank you very much for your attention again.